as electrical engineers are the electromagnetic fields. And if you think about energy stored in an electromagnetic field, you can think of them as being related to this equation. Okay, that the energy stored in the magnetic field is equal to this equation, something that we learned in 350. And if these are electromagnetic fields, then they carry power in terms of energy flow. You can think of this as energy moving through space, giving rise to energy flow, which is power. And these quantities in classical electromagnetics are continuum quantities, which means that you can vary continuously from 0 to as large a value as you want. Okay? But quantum mechanics does not agree with that. Quantum mechanics says that these quantities have to be quantized. You cannot have continuous level of energy all the way from 0 to certain large value. Okay? We see how quantum mechanics affects that these values have to be quantized, not continuum as they are now. Okay? And as you know, the quantized nature of the electromagnetic field was first suspected by Planck's radiation law. He found that he couldn't fit the radiation law unless he assumes that the electromagnetic field is quantized in energy level. And then when he assumed that model, he could fit a radiation law, which is known as the Planck's radiation law. Okay? And that was the first indication that electromagnetic energies have to be quantized. And then the second indication is actually the photoelectric effect proposed by Einstein. That if you have a piece of metal, if you shine light onto the metal, and then you get an electron coming out of that piece of metal with a negative charge. Okay? He found that unless the photon energy h bar omega reaches a certain value, okay, that the electron would not be knocked off the atom unless this h bar omega coincides with the energy that's needed to tear the electron apart. And he found that this quantity that is associated with light is actually quantized. It doesn't come continuously. It comes as a quantized value. Each photon has a packet of energy that is related to h bar omega. And if this packet of energy is enough to tear the electron apart, then the electron will fall apart and leave and go into vacuum. This is known as the photoelectric effect of Einstein. Okay, and this is the second indication that this kind of energy cannot be continuum. Now let's see how we can see this from the mathematics. What happens at a fundamental level is actually the quantum harmonic oscillator. And the quantum harmonic oscillator is the source and the reason for the quantization of classical fields. So what is a quantum harmonic oscillator? Well, if we have a positive charge tied to a negative charge, classically we like to think of them as being tied by a spring, and then this thing will oscillate, okay, as a classical picture. It will oscillate as a classical harmonic oscillator. But quantum mechanically, that is not the correct picture. Quantum mechanically, we should think of a particle being described by this wave function satisfying an equation. And we can think of this equation as 1D. Okay, let's think of this as 1D. Plus v of x is equal to p of phi of x. And this can be 1D function. And this v is something that looks parabolic. Okay? If we have a v of x that looks something like this, actually I use z in my lecture note, so I change them back to z. Okay, this is a one-dimensional problem. And this potential V of z is a parabola. This parabola is defined by half m omega squared z squared. Okay? And it describes a particle that has to go back and forth classically in this potential wall. And if you look at the classical picture of this particle in this potential wall, it will correspond to this other classical picture. But then you can also lift this away from a classical picture and look at the quantum mechanical picture of this particle in the potential wall. In that case, you need to describe this particle with a wave function. Okay, the wave function is a wave function that satisfies this equation. Otherwise, you can just say that this equation, I can maybe describe it with something like md squared dt squared is equal to minus k z kind of thing. Okay, I can describe this equation of motion for that classical object with this, and then I find that z, I will find that d squared z dt squared is equal to minus k over m z. Okay. So if I assume that z is proportional to e to the minus I omega t, then I find that minus omega squared z is equal to minus k over m z. Okay, omega must be square root of k over m. Okay, k being the spring constant. And this omega is the same omega that we have over there. And this same classical equation can be described by this same potential wall, if you were to write this classical equation for it. But the quantum picture for it will be given by this equation over here, with the minus sign over there. Okay? So, quantum mechanically, this will not be a particle, but a wave function of some sort that moves back and forth in this potential wall. And those wave functions can be found in closed form. We show how to find this wave function in closed form earlier in the course. They can be found in terms of Hermite Gaussian polynomials. Okay, they can be found, and it turns out that this is one of the few ordinary differential equations that have closed form solutions. And if the potential is something of this form, this equation has closed forms in terms of Hermite Gaussian polynomials. But today we'll find different ways of finding those solutions for a quantum harmonic oscillator. Okay, we use raising and lowering operators. We use creation and annihilation operators, and find a complete solution to this quantum harmonic oscillator. So what we found actually previously is that classically, if you look at this system, it will have an oscillation that is proportional to something like this, and z is maybe z naught e to the minus I omega t classically. So you can have any kinds of amplitude as it oscillates. But quantum mechanically, we found that the amplitude of oscillation is actually controlled by the energy level E. We found actually equal eigenstates that are equally spaced. Okay, equally spaced. We found that E actually is equal to h bar omega, or n h bar omega plus n plus half h bar omega. Okay. And those are the energy levels that we found using Hermite Gaussian polynomials. And all these energy levels are equally spaced. And there is a ground state energy with n being 0 of half h bar omega. This is called the 0-point energy of these quantum harmonic oscillators. Otherwise, the energy levels are equally spaced. Okay, E0 is half h bar omega then it's E0. E1 would be just one level up by just adding h bar omega. And that was what could be proven previously, but let's solve this equation with a different method, and let's do a change of variable to this equation and letting C being equal to m omega over h bar times d. If you do this change of variables, then what happens is that this equation can be simplified. Okay, it can be written as half d squared equals c squared. This term is still there. Okay, and then this parabolic term, z squared is still there, but simplifies as c squared. And then if we call it wave function psi, and then the right hand side can be written as h bar omega cos c. Okay, it's just a change of variables. If you do that change of variables, that equation, the h squared over 2m has been absorbed, and then some of the constants in front of the potential is also absorbed, and it becomes 1. Okay, I will not go through the detail, but this makes the math a lot simpler. And we can actually factorize. This is something like a squared plus b squared kind of thing. Why don't we try some kind of a factorization to see if we can simplify that? Okay. If we try a lot with factorization, maybe this is a plus b, a minus b. And there's a trick to it though. There's some catch to it. There's a snag to this because a is not a simple scalar number. A can be an operator, a differential operator. So if you try this trick, it will not exactly be factorizable, but you have this extra value. Okay, that half of minus b squared equals c squared plus the c squared. Okay, is equal to a factorized quantity 1 over root 2 d equals c plus cos c. Okay, 1 over root 2 plus d equals c plus cos c. Okay, almost like a plus b, a minus b kind of factorization, but you have to add an extra term. And that extra term is d equals c cos c minus cos c d equals c. Okay, you can convince yourself by just multiplying things out. If you multiply these terms out, you get 4 terms. Okay, 2 of the 4 terms become this. But then dd cos c and cos c do not commute. Okay, they do not commute, so you get these extra terms. Okay, you get this extra term, so you actually have to add this factorization with this extra term to make it equal to that term on the right hand side. Okay, this should be a plus actually. It should be a plus sign over here. Okay. So you can think of this as being something like the momentum operator. This is like a position operator kind of thing. Okay? You can think of it that way if you want. But it's quite easy to show that when you have this operating on any function, d equals c, cos c minus cos c, d equals c, operating on any function of cos c, okay, this is going to be equal to, if you do the first term, it will be f of cos c. If I just work on the first term, f of cos c, and then plus cos c, d cos c of f. Okay, if I just do the first term. And then the second term will just give me minus cos c, d cos c of f. Okay, so you can see that this thing operating on any function is just giving you the function back. So this must be an identity operator. Okay, this must be an identity operator. Can you see that if you work that out? That thing operating on any function of cos c gives you a function of cos c back. Yes?
You use that the second one from top as minus b squared over
yeah, a minus b squared. Sorry. A minus b squared kind of factorization. Yeah.
Yeah, it's just that, right? It doesn't have extra terms. It's a plus b.
Yeah, if a and b are scalars, it will just be that. But because a and b need not be scalar, you will have to add some extra term to cancel the cross terms. Okay, this is the term being added. Because one of them is a differential operator. Okay? And the differential operator looks something like that. So if you just use this simple formula on the right, you don't get the left-hand side because these are operators. They don't commute. And then you get this extra term. You have to add this extra term in order for this to be equal to that. And that extra term is just an identity operator. That's what I'm trying to prove. Okay? So, because of that, then you can actually write this factorization in terms of this factorization. You can write it in terms of being equal to A dagger hat A dagger, okay, plus half. Because this thing, as I showed before, is identity operator. Okay, so you can think of this as identity if you wish to, but it's just half. Okay, where A dagger and A, okay, is equal to 1 over root 2 minus B because C plus to C. Okay, and then A hat is just 1 over root 2 B because C plus the C. Okay, and you can show that these two operators, A hat dagger and A hat, are the conjugate transpose of each other, or they are the Hermitian transpose of each other. Okay, or another mathematical name for it is that this operator is a joint of this operator. This operator is the joint of that operator. And we learn how to define a jointness. Okay, the jointness means that if you have, say, F, and then if you have G, okay, by the definition of the jointness, this is the same as A dagger F G. Okay, if you have this property been satisfied, then you can show that this is actually the joint of this. If you plug this into this inner product and manipulate around, okay, because this term is actually the joint of this term. This term is self-adjoint. Okay, this term is self-adjoint. So because of that, if you write things in terms of these simplified operators, that equation of motion or equation Schrodinger equation that looks like that can be greatly simplified. It can be written as A hat dagger A hat plus half psi is equal to E over h bar omega psi. Okay, and this A hat dagger is called the raising operator. For reasons to be explained later, is also the other one is called the lowering operator. Okay, it also has a name of creation operator. It also has a name of annihilation operator. Annihilation. Okay, so they are the same thing. Yes?
How do we know that A dagger and A that's conjugates just from
Conjugate transpose of each other, which is the Hermitian transpose.
we're just trying to take the complex conjugate of A dagger. I find it a little bit hard to get a.
In your homework, remember you are asked to prove that P hat is a Hermitian operator, right? P hat, remember, was I h bar d x, right? Something like this, right? And this together, you're asked to prove in your homework to be a Hermitian operator. Okay? But this is self-Hermitian. If you remove the I, it's not self-Hermitian anymore. This is the conjugate transpose of this. This is the conjugate transpose of this.
So you will just remove I.
You remove the I, it becomes non-Hermitian. Okay, so this is not self-Hermitian anymore.
Oh.
Okay, but you take the Hermitian transpose of this, you get this. You take the Hermitian transpose of this, you get that. Okay, you can go through the same exercise as you did in your homework, where you were asked to prove that this is the Hermitian operator. But without the I, it's not Hermitian. Okay, it's not Hermitian anymore. And it has this property that the Hermitian transpose of this is that, the Hermitian transpose of this is that. Okay? You want me to go through the proof? I can prove to you quite easily.
Yes.
Huh?
Yes.
You have proved before, right? You want me to go through the proof or?
Yeah.
Okay,
Yeah.
let's prove it then, okay? And this transpose or conjugate transpose is an abstract concept when you apply that to differential operators. Okay, so what we need to show is that in the case of matrix algebra, you will have something like B. Okay, if you want to find the Hermitian transpose of this, what you do then is to write this as this. Okay, if you write that as that, okay, it is the same line as above, right? If you take the conjugate transpose of this, you get this thing. Okay, I can rewrite it, but this means that the operator that you plug in here has to be the conjugate transpose of this operator. So let me use the same notion to define the conjugate transpose. So if I have F, and actually I just need to prove this piece along. Okay, F d to C from G, and this would be equal to d to C, F of the C, d to C, G of the C. Right? With the conjugation sign over there, because these are direct notation with inner product. Then I can apply the integration by parts rule, integrate this, then I will have, for the first term, G of the C, okay, minus D of the C, D to C of F of the conjugate of the C, G of the C, right? And this one would be evaluated at, say, the two endpoints which we pick to make the function goes to 0. And let's always pick this function so that we have 0 at infinity or some endpoints, so that we are left with this integral, okay, minus d to C F conjugate of the C, G of the C. And then I write this using direct notation again. It will be minus d equals C F G of the C. Okay, so it proves that this must be the conjugate transpose of this quantity. Okay, by the definition of what the conjugate transpose is. If you were to define in matrix algebra what the conjugate transpose of this without index, using indices, of course you can say conjugate transpose is this. Okay, but if you don't have index to play with, in the case of a differential operator or integral operator, you have to use this definition to define what the conjugate transpose is, because we don't have indices to play with. So if you use this definition of conjugate transpose, we go to this mathematics. Okay, find that if I put this on the left-hand side, this piece here must be the conjugate transpose of that. Okay? So if this piece is the conjugate transpose of that, this must be the conjugate transpose of that. That must be the conjugate transpose of it. This piece is quite easy to show. Okay? So the annihilation operator and the creation operator are the conjugate transpose of each other. They are not self-adjoint, which means that they are not Hermitian. Some mathematician likes to use the term self-adjoint, which is the same as saying that the operator is Hermitian. The matrix operator is Hermitian. Okay? So, with this in mind, then we can actually rewrite Schrodinger equation for a quantum harmonic oscillator in a very succinct manner. And that, as I said before, it becomes very succinct. Hamiltonian becomes very succinct. Plus half. Okay. We also have this very simple commutation relationship that follows from here. If you plug this and uses that commutation relationship, you can actually show this. Okay, you can actually show that this is true. That A hat minus A hat A is equal to I. Okay, this can be shown very easily because of this property. Of this means the second piece is very simple. It self-commutes. Okay, it's not an operator. If you plug the second piece into this, it gives rise to 0. The first piece gives rise to something that looks like that. And then you can show that this is the identity operator. The annihilation and the creation operator look something like that. You want me to show this, or is it quite obvious? Obvious, right? Obvious from this property, right? I don't need to show it. So another way you can write this thing is actually to write this half being equal to A hat A minus A over 2. If you plug that in, another way to write the Hamiltonian is to write it in this manner. Okay. Is to write it in this manner, and this is kind of interesting because it is symmetric with respect to the two terms. Symmetric with respect to the two terms, you can see that you have some niceties associated with that. And then if you write down E sub n previously, the n plus half over h bar omega. Okay? And you can define a number operator. You can call this a number operator. That has a property that the number operator operating on the number state, the eigenstate of the Schrodinger equation just returns you the number n. Okay, it just returns you that. Okay. And let's prove the raising and lowering properties of this annihilation and creation operators. Sometimes they also call, I think, creation and destroyer, destruction operator or something. Creation and destruction operator, but annihilation sounds better, right? Annihilate. But if you don't like the words, you can say it's just raising and lowering operators. Okay? Let's prove the raising and lowering properties of this operator. That if we have a number state, that if we operate on this number state has this property that when it is being acted upon by the number state, we just return n psi n. And a lot of physicists will just write this as n, okay, shorthand notation. Okay, but this means that, okay, the number state. And let's prove that this actually is in fact a lowering operator. So if we now measure the number of photons or energy state that we have after it has been operated on by the lowering operator, let's see what the eigenvalue of this system is. Previously, when this thing acts on a number state, okay, this is called a number state, it just returns the number n, the energy level that is in. We want to show that this will return something less than n or equals to n minus 1. How do we show that? To show that, we first use this commutation relationship between the operators and write this as being equal to a hat minus 1. Okay, I just wouldn't write this as identity, I just write as 1. A hat psi n. Okay, if I write it as such, then and then I can actually pull this in here and then pull it back out again and write this as A hat A minus 1 psi n, right? What I do is that pull this in, and then pull this out on the other side. Okay, I just get this. Okay? If I get this, then this is the number operator. Operating on the number state, it just gives me n. So this gives me n minus 1 psi n. Okay? So you can see that the eigenvalue associated with this thing, when it's been operated upon by the number operator, just give me an eigenvalue that's one smaller. Okay? So what you have then is that the lowering operator, when it operates on the number state, must give rise to a number state that is one number smaller. Okay? Another way that physicists would like to write this is that this is into the a n minus 1. Okay, they mean the same thing. You must have lowered the eigenvalues of that state by 1. Is what it means if you look at this one. At A operating on this is equal to that, and it's equal to that, it's equal to that. It gives you an eigenvalue smaller than 1. Okay? It doesn't return you n. And similarly, you can show that A dagger A operating on something that has been operated upon by the racing operator. This is called the racing operator. And again, using the commutation relationship that we have, replacing A dagger with 1 plus this quantity. Okay, you will have 1 plus A dagger A, making psi n. Okay. And now I put this through. It doesn't work, right? Let me see. It gives me n, right? It gives me, this would give me n. Okay? So I have A dagger n plus 1 times of n. Okay? And then I can see that this racing operator, when it operates on the number state, will give me a new state. The new state has the new eigenvalue of n plus 1 when operated upon by this number operator. Okay? So my conclusion is that the racing operator operating on the number state must be equal to the number state that has been raised by 1, but with the constant that I do not know what it should be. Okay? I do not know what the constant should be. Okay? Now we try to find these constants. An and Bn. In order to find this constant, we would like to multiply this equation by psi n minus 1 from the left. Okay? If we multiply that equation by psi n minus 1, then what I have is that psi n minus 1 psi n.
Are we supposed to have a n minus 1 because the b coefficients follow the psi function? And the
Here,
right
psi minus 1.
Yeah, because b n plus 1 versus a n. Which notation should be observed?
I don't think it matters because I call them by different names.
Okay.
Okay, B, I let this subscript follow this. A, I let this subscript not follow this.
Okay.
Just deferring by one. Let me see what I get. Okay. So if I do that, then by the normalization property of this eigenfunctions, I just have an on the right hand side. Okay. And then if I multiply this equation by psi n plus 1, and then by the normalization property of the eigenfunctions, I have n plus 1 here, and then a dagger psi n must be equal to bn plus 1. Okay. Now I lower the index by a little bit. Okay, I will get this equation psi n minus 1 is equal to bn. Okay, I can take the conjugate transpose of this equation. I can take the conjugate transpose of this equation. I get this quantity over here. Okay, you agree that the conjugate transpose of the left-hand side is equal to that. You think of this as three vectors, vector matrix vector. You take the conjugate transpose of this, you get that. Think of this as a matrix operator. You get this Hermitian transpose. So now the left-hand side are equal to each other for these two equations. You must have the conclusion that an must be bn conjugate. Okay? But then you know this fact that a dagger a times psi n is equal to a dagger sine n minus 1. Okay, because this is a lowering operator. It lowers this by one number state. Okay, and then this is a raising operator. It raises it by one number state. So this must be true.